Good morning. Welcome to Krishna's class. Last time we proved the Holder's inequality and the Minkowski inequality. Now I had earlier said that these are all tools for proving some or exploring the structures of LP spaces. And one of the consequences is that now LP with first of all we observe that norm so see for F belonging to LP for F belonging to LP we have the functional infinity, and one observes that this defines a norm. So this is norm is a function. Of course, there is a corresponding result for norm F infinity. This is defined as the essential supremum of now what one can prove is the following. So let me just designate it by norm P is a defines a functional norm in all cases it defines a functional because it is not a linear functional. This is not a linear functional. But what we have proved is this, what we have F equal to 0 means F is equivalent to the belongs to the equivalence class containing the 0 element. Of course, this one, this is 2. And this result. Therefore, it satisfies the first condition for this function to be a norm. The second condition is that we have this is by Minkowski. LP. This is by Minkowski inequality, and this is where we need the Minkowski inequality. And then, of course, this is proved. Therefore, if you carefully look at what is happening, just want to make a remark. Define a functional. In this case, we are saying how it operates or interacts or what it gives when you add, because addition is one of the operations that you have in LP as a vector space, and on that how it acts, and that is what is contained in the Minkowski inequality, and then how it interacts with the scalar multiple. What is the norm of the scalar multiple of F, and how is it related to the norm of F? Okay, so it satisfies all the three criteria for for this functional to be a norm. Consequently, is a normed yes. That is a pre-Banach space. You could say that it's pre-Banach space because with one more condition, it becomes a Banach space in the sense what we would have to prove for that is that LPE is a complete normed space. That is our final objective, and we are inching towards that. But in between, we are seeing a lot of things happen. Now let us see. Let us look at a special case. The special case we are interested in is the one where P equal to 2. The special case is this. So we now consider then what you have is the L2 space. With now endowed with now this is of course specific case. It's a normed space. It has more fascinating structures, and it turns out to be what is called an inner product space. This is an inner product space. That is, or what you call a pre-Hilbert space. Both are the same. Pre-Hilbert space is something linear space where the parallelogram law holds. Okay, that means what you call a pre-Hilbert space, what you call an inner product. Let us look at one by one. An inner product space. So you have X over, let us talk about the real inner product space over R. One can as well define things for C. This can be generalized to more exciting spaces. So to see that the real vector space is a real now define the inner product, what you call an inner product from X cross X R with the following properties. With the following properties. The following properties. The first one is that it's a real number for every xy belonging to X. Is linear in each of these arguments. X. Third one, symmetry. X. That is the symmetry. This is what is called symmetry. Now we'll have the fourth property, namely these four properties. Now one more thing that you have here is that is greater than 0 and equal to 0 implies x equal to So you have, this is what you call a real vector space. Or now, this is what you call an inner product. This is called an inner product only. So X with an inner product is called an inner product. So any linear space over R with an inner product is called an inner product space, the real inner product space. Now I think I want to make some remarks about it at this stage. Or we will look at the consequences of this. So now define So let me define this. Then and hence is a normed linear. Therefore, it is also a metric space. And every normed linear space a metric space. With norm defined with the distance So this is an inner product space. It's a normally linear space, and therefore it's a metric space. Therefore, it has a topology. So it's a topological vector space. And you can talk about all sorts of topological properties. Completeness comes this. Now let us also see, I was telling in the beginning that we are considering only the field associated as R. But one can generalize it, and quite often the most useful situations we have what are called the complex vector spaces. So the more generally what you have is, if we take R Instead of R, consider C. I mean, it is possible. So this is a real inner product. Now we complex inner. X over x. Now define an inner product as a map C with the following property. The first one is second property is greater than or equal to 0, and if and only if x equal to 0, we I said for we have earlier done it in our discussion on inner product space of these aspects. I am just recalling in this context and then connecting, trying to connect what we have done so far. For this is the conjugate symmetry, namely x this is where things depart from what we did for the real inner product space. The complex conjugation was not there, but you can see that essentially this is a generalization of what we have done there. For every belonging to X. The point is so these are the properties that are satisfied by the so-called inner product, complex inner product. Now you see that if you were to take C to be R, that means if you are considering the real inner product space, then you can see that this in fact completely coincides with what we did earlier. Now we make some remarks. Some consequences are x alpha y equal to alpha conjugate alpha belonging to C. This is something which can be very easily proved using the conjugate symmetry condition. That is this conjugate symmetry condition. Maybe I do this and right. Conjugate symmetry condition and this side. Okay. Consequently, what you have is this. Further, inner product of x with x is greater than our. Okay. And of course, equal to 0 means x equal to 0. Because inner product of x with x equal to inner product of therefore is a real. That's a consequence. Further, one can show that, and of course, we have earlier put the restriction that this is to be positive. So, we define let me write this. This is the situation when the associated field is C. And what we considered as the real vector space or real inner product space is a very special case of this. Okay. So, in general, we often use this, although in the discussion that we have undertaken, we have been considering only real valued functions. But you can always generalize in a very natural way all those things to complex valued functions and you know and a complex inner product. Okay, right. One fascinating inequality that we have often proved in this case is this. You see, this is all generalization from our familiar R2 or R3 with the dot product. So let me just make a remark here. Inner product on a vector space is a natural of the concept of dot product on now we know that if x is equal to then x dot y is defined, this is the dot product. See? And this is all the properties of an inner product. And this is a real number and which has say map from x cross x. So the dot product is a map from x cross x. In this case, if we were to replace this by C2 and C3, then these are complex numbers, and then x dot y is defined as x1 y1 conjugate plus x2 y2 conjugate plus x3 y3 conjugate. Now we have seen this. Then you can say you get a what you call a complex inner product space. Further, we have this result. For every xy, x with the inner product, right? For dot product, and the obvious interpretation of this, which are very familiar. Now you see that now we consider L2. So we define on this now one can prove that endowed with a norm square, that is f dot. So this is a norm, and in proving that the property that this is the Minkowski inequality for that. Okay. we use the so-called Cauchy-Schwarz rule. It is generally available in any inner product space. That is, which is the special case of Holder's inequality. So we shall formally write this, to write it as a theorem. Let Krishna will say and F1GD functions on for which f square d square are integral. That is f. This is the meaning. Then their product Fg is also integral on on E and we have taken over just a minute. That is, we define something that, and whatever we have proved so far, this is the special case of L2 so the corresponding Minkowski inequality. The corresponding Minkowski is where So if we set then on consequence form load further say simplicity. Simplicity is Now this is a metric space. Now the question that we of course ask is more generally, is LPE with where BP is this a complete metric space? So this is the question that we have. I think that's a nice place to stop. So we obtain some estimates in the next lecture, and then our task will be to answer this question. It is actually the crowning glory in recognition. Thank you very much.